Okay, so now if I'm given the correspondence, this is the correspondence. I'm given the correspondence. 300 corresponds to 40. 1000 corresponds to 60. This number corresponds to that. This number corresponds to that. If I'm given the correspondence, very easy, I can identify functions or not. What if I'm given graphs? Given graphs. Can I identify functions? Here's a couple, or a few graphs. Okay, can anyone tell us whether the first graph represents a function? Yes. By the vertical line test. For this x value, I read only one y value. For this x value, I read only one corresponding y value, where it crosses the function. For this x value crosses the function, I only read one y value. Are these two functions? Function, function. What about this one? No. By the vertical line test, for x equals 5, let's say, the line crosses the graph in 2 points, therefore a relation, not a function. Possible in real life, yes. A function, no. What about the circle? Is the circle a function? No, actually it's two functions, the one from the top and the one from the bottom. So relation. So if I'm given the correspondence, I can identify a function. If I'm given graphs, I can identify the function or a relation. Any questions? Any questions? And not a function, a relation. The circle is a relation. So I'm on page 7, 8, 9. Okay. The next step that I would like to continue with, or the next topic, is how to find the x values and the y values for a function. For a relation as well, we can. But mainly I'm interested in functions. So let's suppose I have this graph. I'm going to put some numbers in there. Okay, is this a function?
Yes.
By the vertical line test, I would say this is a function. By the vertical line test, this is the graph of a function. Perfect. Now, I would like to know what x values does this function, for which x values this function exists. So in other words, if I want to ask you find where this function crosses the y-axis, where it crosses the y-axis, will you be able to find it? 0, 5. If I ask you, do you think that the function exists when x is negative 10?
Yes.
How do I know? Because of the arrows, correct? It will continue forever to the left and right because of the arrows. So yes, it will exist. What if I ask you when x equals 100, will the function exist?
Yes.
What if I say x equals negative 1,000?
Yes.
So what kind of values can this, for this function, what kind of values will it have, will it take? I mean, what can I replace x by? For which x values does the function exist? Very good. That is called domain. Domain is the set of values of x that can be plugged in the function. The set of values of x is called domain. And here's how we write a domain. Negative infinity to infinity. Perfect. Everywhere. Everything here. Everything on the x-axis is part of the domain. Perfect. Now, what do you think I'm going to ask? Of course, the y values, right? Perfect. So y values. The y values are part of a set called range. Is the set of values of y. Now let's come back to this graph, and please tell me what are the possibilities for y. Remember, we read the domain on the x-axis. We read the range on the y-axis, from the smallest possible value for y till the largest, like we do it with the x, from the leftmost possible x till the rightmost possible x. But for the y, for the range, for the y values, then we go from the smallest y value to the largest y value. By looking at this graph, can I identify what is the smallest possible y value? And what is the largest possible y value? Correct. Very good. So we write a range, bracket, -2 to infinity. Very good. That's how we determine the domain and range from a graph. Of course, we're going to look at a few more examples. However, I would like to talk about the function notation now. Function notation. We just used it a few minutes ago. Not 2 minutes ago. Last time we met. I don't have it. Okay, here it is. Which problem from 1 through 7 uses a function? Number 4, of course. This is a function. So the function notation can be anything you want, really. F of x. We do not read f times parentheses x, right? This is f of x. It's the name of a function. It can be temperature function of pressure. It can be pressure function of, or price function of units. It can be age function of time, or average function of time, and you name it. Now, let's start with f of x. Where is x measured? I know it's a silly question. We just talked about domain.
X.
On the x-axis. Where will y or f of x? It's the same thing, y or f of x. And you can say, why do we need two notations? Because one is more convenient than the other in different situations. So where will I measure f of x or y? It's silly. It's a silly question, f of x. Good. So this is called independent. Independent variable. What do you think this is called? Right. It depends on x. So here, t of p. P is the independent. T is the dependent. P of x, x the independent, p the dependent, and so on and so forth. And you can give them any meanings you want. Okay, how to read a function? How to read a function. So I'm going to denote it by f of x. Please give me any function that comes to your mind. Anything you want. If not, I will make one up.
3x plus 7.
Perfect. This is very important to understand. And let me also give you another example that is a little bit more difficult, way more difficult. Let me show you what I see when you give me a function like this. For f of x, I see this. For g of x, I see this. Because now if you ask me to evaluate a function, I know what I have to do. Since you gave me f of x, if you ask me to find f of, make a number up, any number. Very good. Then I know what I have to do. Look what I'm doing. That's what I'm doing. I'm finding f of 3, which is 3 times 3 plus 7. So that's 9 plus 7, 16. If you say, no, I want you to find f of 0, then I will say 3 times 0 plus 7. And I will get 7. If you say, no, I don't want you to find f of 0 or f of 3, I want you to find f of x plus h. And I'll say, what? Oh, no problem. It's the same pattern. All I have to do is put a parenthesis. So then f of x plus h. Now this is x plus h. Therefore, this must be x plus h. So I have 3 parentheses, x plus h plus 7. No problem. I can evaluate it for whatever you make up for me because I see the pattern. The pattern says f of whatever you want equals 3 times whatever, the same, it has to be the same whatever, plus 7. The same thing here. If you ask me to find g of 0, I'll say 0 squared is 0, 0 plus 3 is 3, 0 minus 4, and I'll say g of 0 is negative 3/4. If you say find g of a plus 1, no problem. A plus 1 squared plus 3 over a plus 1 minus 4. That's all I had to do. I replaced this by a plus 1, this by a plus 1, and this by a plus 1. Because the pattern of this function is g of whatever, whatever squared plus 3 over whatever minus 4. And by the way, since we signed an agreement last time, how much is a plus 1 everything squared?
A squared.
Very good. You're falling behind if you don't know this by now. So please be careful. Good. Any questions on this? Any questions? I want to go back to 3.6 because I browsed towards the end of the book. 3.6. And I want to look at a few examples of functions and discuss their domain without having graphs, without having the correspondence, and without other analysis, but just the function. We are given the expression. Let's see how we handle that. And that is, I would like to start with g of x. That's number 64 on page 236. And we are given g of x equals 5 minus 2x. And then I would like to look at 65 on the same page. I'm copying them down so I don't have to look at the book. 1 over x plus 5. And also 67 on the same page. You don't have to write more than the first one just yet. G of x equals the absolute value of x plus 1. Ready? I'm given these functions. I'm given g of x equals 5 minus 2x, and I am not asked to graph. I'm only asked to find the domain. And I don't have to do anything. I just have to look at the function and think, okay, what can I replace x by? That's the question on the domain. You don't have to do anything for this one, anyway. You just have to think, okay, 5 minus 2x, can I plug in 0? Yeah, I'll get 5. Can I plug in 1? Yeah, I'll get 3. Can I plug in negative 2? Yes, I'll get 9. Can I plug in negative 10? Yes, I'll get 25. Can I plug in 15? Yes, I will get negative 25. Can I plug in blah? Can I plug in anything? Is there any restriction on x? Is there a particular x on the entire real line that if I plug it in, I'll say, oh no, I cannot give you an answer? Is there one? No. So what do I conclude about problem 64? What is the domain of g of x?
Negative infinity to infinity.
All real numbers, excellent. This is always true for polynomials. Note, all polynomials, degree 1, degree 2, degree 3, degree 4, degree 5, any polynomial, all polynomials are defined, or we say have domain, in other words, are defined on negative infinity to infinity. All polynomials have domain, everything, no restrictions. I want to jump to 67, and then I'll come back to 65. So let's look at 67. The same question. I'm not asked to do anything. I'm asked to think. Okay, can I plug in anything in x plus 1 and then apply the absolute value to it? Let's say 0. 0 plus 1 is 1, the absolute value 1. Negative 10. Negative 10 plus 1 is negative 9, the absolute value 9. I'll give you a number back. 1500. Yes, 1501, the absolute value is 1501. So is there any potential problem here? No. So what will I conclude about the domain of G? Negative infinity to positive infinity. Okay, perfect. Now let's look at 65. So this was a linear function. This is what? An absolute value function, right? Because it has an absolute value. This is a linear function, and this is the absolute value function. Absolute value. Linear. Okay, perfect. So now let's look at 65, h of x. What can you conclude about this? What type of function is this? What do you think? I saw the absolute value, and that's why this is the absolute value function. What do I see here that I don't see here, for example, and I don't see it here? What is special about this, and I don't have it here, and I don't have it here? Right. So it must be a rational function. It has a ratio, and it has x in the denominator. Careful, this function is not rational. It's linear. It's nothing else but 0.5 multiplied by x. So if you see a fraction that does not have x in the denominator or the variable in the denominator, that cannot be a rational. This is linear. This is a rational function because it has a ratio and because it has x in the denominator. X over 5 is not rational because it's 1/5 multiplied by x, 1/5 multiplied by x, or 0.2x. So x must be in the denominator for a function to be considered rational, and that is the case here. So now this is a different story. Here's how I think now for this function. Here that was linear, anything goes, no problem. Here it's absolute value. Yeah, I can, if I get anything from x plus 1, which I will get, then I can apply the absolute value to it, no problem there. But here the question is different. Oops. Can I really divide by any possible number? Is there a particular number that I can never divide by? That's the question here. So if this is 0, 1 over 0 is undefined. What value of x makes this number 0? Correct. So I will put aside a condition. X cannot be -5. Therefore, the domain of this function cannot be all real numbers. And now I know how to write this domain because I studied the AND and the OR operations with sets and intervals. How do I write the domain of this function? It cannot be everything. I cannot write this. From here, I must exclude -5. Because -5 plus 5, if I ask you to evaluate this function for -5, you'll say, sorry, I can't. Because -5 plus 5 is 0, 1 divided by 0 does not exist. So how do I write the domain? Using interval notation, and of course, what will I use? Union or intersection? I can't. I can't use the intersection. They will not intersect. It has to be the union. So the domain must have the union in the middle. What is the left interval?
-∞ to -5.
5 with a parenthesis. Don't make the mistake to write a bracket. I'm not saying you did, but you cannot use a bracket because the bracket means it includes -5. Union what? Exactly, to infinity. This, in plain English, means everything but -5. Exactly. Any questions? Any questions for me? Any questions? Any questions? Okay. Yes. Say it again. I couldn't hear you, Becky. Oh, no, no. No, I would not do that. Sure. Okay. I would like to ask a couple of questions on a different function. I'm going to use the same function, actually. It's very clear. So I'm going to copy the same function. And I think we had 6 here, and I think we had 8 here, and -2, and I think we had 5 here. And I am going to ask you to find, so now I know that this is a function, so I'm going to call it exactly f of x. And I am going to ask a couple of questions. Question number 1, Find f of 0. Question number 2. You don't have to write them, we'll write them together. F of 6. Question number 3. Find x when f of x is 0. And question number 4. Find x when f of x is negative 2. What are all these questions? A few minutes ago, we looked at the domain and range for this function, and we decided the domain is all real numbers, and the range is between negative 2 and infinity, correct? Okay. I'm asked to find f of 0. What will you say or do? Let's think. In order to find f of 0, I am given what? Am I given x? Am I given y? What am I given when I'm asked find f of 0? I'm given x. Very good. So x equals 0. How do I graph a line, not a point? Because x equals 0 is not a point. It needs the y coordinate. So when I say x equals 0, I mean a vertical line. So I will draw the vertical line x equals 0. This is it. Does it cross the graph in a point? Yes, right here. 5. So which point did we really read from, to be exact? Comma. That's it. Now I'm asking you to find f of 6. Again, what is given in our question? X equals 6. So then again, I don't have to draw it, but I imagine that I'm drawing, at least imagine I'm drawing a vertical line that is x equals 6. It crosses the graph of the function in this point, and there I will be reading the y coordinate. What is the y coordinate? 0. What ordered pair did we just determine? Good. Very good. Excellent. Now I'm asked to find x when f of x is 0. Now I have to think for a moment. What am I given now? Yes. But how do I graph y equals 0? Exactly. So y equals 0 is this. Does this line cross the graph of the function? Yes, it crosses here and here. Therefore, I will have to give two answers. X equals how much when y is 0? And x equals how much when y is 0? That's it. So for number 3, can anyone give us the ordered pairs that we read from? Excellent. Perfect. So now final question here, number 4. Find x when f of x is negative 2. What am I given now? What does that mean when I say f of x equals negative 2? What am I given? Very good. And I know how to graph this. Again, this is not a point. A point has x and y. If I'm told y equals negative 2, I mean this. This is y equals negative 2. Does it cross the graph of this function anywhere? Good, indeed, at 7. So then there is only one x equals 7. And which ordered pair did we read from? 7, negative 2. Very good. Excellent. Any questions? Any questions? I want to look at one more example of a function, or not. You'll tell me in a moment. So graph this with me. Four on the x-axis, 3 on the y-axis. And let's put this point, 1, 1, 1, 3, 2, 2, and 4, 0. 1, 1, 1, 3, 2, 2, 4, 0. I am going to ask you, please tell me whether this, and we cannot connect the points. Some situations will not allow us to connect points. So my question is this a function? No. How come that it's not a function? Because when x is 1 by the vertical line test, how many different y values will I read? 2. Not a function. However, it's a relation, that's fine. I'm going to ask you to give me the domain of this relation and the range of this relation. We can always determine the domain and range. It's not what we want, it's not a function, but we can still find its domain and range. So can anyone dictate the domain? And it cannot be written with interval notation, because those are points that are not connected. We have to use braces for that. Okay, so can anyone dictate the domain of this relation?
1, 2, 4.
Exactly. 1, 2, and 4. This relation exists at 1, it exists at 2, and it exists at 4. Excellent. Can anyone give us the range of this relation? If it were a function, I would have done the same thing. So if it's now the range of this relation, 0, we're measuring them where they are found on the y-axis. 0, 1, 2, 3. 0, 1, 2, and 3. Very good. Very good. Now I want to introduce one more thing about these functions. And you will tell me what I mean by this. Here's a graph, and I would like you to establish whether it's a graph of a function or not. And I'm just going to make up some numbers here. I'm going to say -2 and 8. Question, is this a function?
Yes.
By the vertical line test, this is a function. Correct. Function. I'm going to call it f of x. Perfect. Now I would like to ask, what is its domain? So remember, from the leftmost point where the function exists till the rightmost point where the function exists. What is the leftmost point? -2. And the rightmost point? Now we have to establish what we use. This point, it says to me, it does not exist. This point says to me it exists. So what, parenthesis, very good, and the bracket at 8, that is the domain of this function. What does this point mean? It means that the function gets extremely close to the value of x, or the value of x in the function gets extremely close to -2, like -1.9999999, but not -2. The function is not defined at -2. It doesn't exist at -2. Okay, what about the range of this function? So this is like a minimum here, and I establish -6 as being the minimum. And this is like a maximum somewhere, and I established a 7. So what will you say? This point exists, and this point exists. So what would be the range from the lowest possible value of y till the largest possible value of y? Both exist, so we have to use brackets. Okay, I just want to show an example that is in your book, and I really like it because this is a very interesting, and we will graph these functions later in chapter 8. So this is a very important type of function. Piecewise-defined functions. Yeah, I know I have 5 minutes left. I didn't forget. Okay. So here is the first example I gave you about functions. If I talk on the phone for 300 minutes, I will pay, no. If I talk on the phone between 300 minutes and 400 minutes, between 300 and 400, I will pay $30. If I talk between 400 and 500, I will pay 32. If I talk between 500 and 600, I'll pay 35. I'm just making numbers up. That is a piecewise defined function. It's defined in pieces. If x is between this and this, a certain function. If x is between this and this, another function. If x is between this and this, another function. Here's another example. We all pay taxes. And we have to turn in our taxes between today and April 15th of next year, right? I'm making numbers up. I don't know the exact correspondence. But if somebody makes between 40,000 and 50,000, let's say, pays 10%. If that person makes between 60 and, or next, what did I say, 40 and 60. Between 60 and 80, pays 15%. Between 80 and 100, 20%. This is a piecewise defined function. For certain values of x, a certain outcome is, a certain function is used. So a piecewise defined function, an example of a piecewise defined function is what is called, so an example is a step function. It looks like a step. Postage stamps are also, or posted when we send a parcel somewhere. It uses a step function or a piecewise defined function. And I'm copying it from page 239. And I'm looking at the top page, problem 38. And I'm just going to copy, this is for postage stamps and parcels. For large envelopes, actually. So at point 8, the graph looks like this. Between 1 and 2, and so on and so forth. Sitting. Page 239, right here. Page 239. 236, I'm sorry. How did I come up with that? I'm not sure. Problem 38 at the top, sorry. What does this mean? Let's read. Let's try to understand it. And then we can answer a couple of questions. It's 8:14. I just would like just to understand it. And then on Tuesday we'll answer some questions. What does this mean? If I send an envelope, this is in ounces, and this is dollars. If I send an envelope that weighs between 0 ounces and 1, I will be paying 80 cents. If it weighs between 1 and 2, but not 1, a little bit more than 1 and 2, including 2, I will be paying $1. If it weighs not 2, but a little bit more than 2, and 3 including 3, I will be paying $1.2. So this is the piecewise defined function. A different function is used for different x values. So between 0 and 1, I have this function, which is not the same with this function, which is not the same with this function. Between 1 ounce and 2, I'm using this. Between 2 and 3, I'm using that. So that's a piecewise defined function.